Okay, so notes 5-1, we're going to kind of copy the big thing on the wall over there. So at the top is relation. And remember, a relation is any set of ordered pairs. Okay, so down from that, we break relations into either being functions or not functions. And the way that we tell a relation is a function is because the x doesn't repeat. But if the x does repeat, it's not a function. Okay, so that's where we left off at the last unit. But this unit is going to be breaking functions apart. Okay, so functions then can be classified in a couple different ways. All right, the first thing that we're going to look at is to see, is the function linear? Okay, so if the function is linear, then it has a constant rate of change. And if the function is not linear, then it does not have a constant rate of change. Okay, so the key part of today is determining if functions are linear. That's what we really want to know. Is a function linear? So that's our first blank right here. A linear function is a function whose graph forms a straight line. So if it's linear, it makes a line. That's what we're looking at. Okay, so this is a graph, right? And we're going to look and see, first of all, is the graph a function? So the way that you tell if a graph is a function is you draw a vertical line, and you don't have to do this on your paper, just kind of hang with me here. Okay, you draw a vertical line and you move it around, and you see if there's anywhere on the graph that you can get this line to touch it more than one time. So because I can't make my line touch the graph more than once, then that means yes, the graph is a function. And the reason is because it only touches the vertical line one time. Oops, one time. Okay, and is it linear? Well, yeah, it makes a line, so yes, it's linear. Okay, so let's look at example 2. Okay, on example 2, it says, is this graph a function? So same thing. I draw my vertical line, see if it passes the vertical line test, and I can't make the vertical line touch that curve more than once anywhere. So I would say yes, it is a function. And the reason is it only touches the vertical line once. And when I look at this graph, it says, is it linear? So looking at that, I can see it's not a line, right? So because it's not a line, it's not linear. Okay, so then with example 3, okay, with this one, when I draw a vertical line, like I can draw it right on top of it. So it's not a function. And the reason is a vertical line touches it infinitely many times. infinitely many times. And that's it, right? Does it say, is it linear? No? Okay. All right, so let's flip over and look at example 4. On example 4, it says, is this graph a function? So this one would be a function for the same reason. Okay, when I do my vertical line, I can't make it touch anywhere more than once, so yes, it's a function. The reason is can't make vertical line touch more than once. And it is linear because it's a graph of a line. So as long as it's a graph of a line, then it's linear. On example 5, when I draw my vertical line, I can't make it touch that horizontal line more than once. So yes, that one's a function. And I'm just going to write VLT for vertical line touch because we've written that about 17 times now. And is it linear? So it's a line, so yes, it's linear. Then on example 6, when I draw my vertical line, I can make it touch twice, a bunch of times. I can make it touch twice right there. So this one is not a function, and the reason is it touches the graph twice. And this one's not linear because it makes this curvy deal right here, so we would say no. Okay, so changing speed a little bit here. Now we're going to look at a table and see how to decide if a table represents a linear function. So on a table, what you have to do, first of all, ask, is the table a function? Remember from a minute ago, we decided that a function is when your x does not repeat. So here, all of my x's are different, so therefore it is a function. And the reason is x doesn't repeat. And then it says, is it linear? Well, if you remember back to one of the very first things that we wrote down here in our little chart, so you can see it, okay? I can tell that a function is linear when it has a constant rate of change. So what we're going to have to look for in our table is to see if there's a constant rate of change. So remember, the way that you find the rate of change is by looking for the change in y over change in x. That's the thing that we learned in the last unit. So I look at my y values. I can see that from 9 to 12, it changes by 3. From 12 to 18, it changes by 6. And then from 18 to 27, it changes by 9. Okay? And then I have to come over here and do the same thing with my x's. So from 1 to 2, it changes by 1. From 2 to 4, it changes by 2. And from 4 to 7, it changes by 3. So we look at each change in y over change in x, and we're looking to see if they have the same rate of change. So change in y over change in x is what we're looking for. So for this first pair, I do 3 over 1, which I can reduce to 3. Then on the second one, I do 6 over 2, which again reduces to 3. And then on the last one, I do 9 over 3, which I can also reduce to 3. So because we were able to reduce and get the same value each time, it has a constant rate of change and therefore is linear. So our answer to this question right here where it says, is it linear, is yes, it's linear because it had the constant rate of change each time. Okay, so then on example 8, we're going to do the same thing. So to see if it's a function, We just have to make sure that none of our x values repeat. So we have no repeating x values, so yes, it is a function. And the reason is no x values repeat. And on the is it linear, the way that we find out if it's linear is we have to see about the delta y over delta x. We have to look to see if it has a constant rate of change. So I'm going to look at my y first. From 12 to 17, that changes by 5. From 17 to 22, that changes by 5. 22 to 32, that changes by 10. And on this side, from 1 to 3, it changes by 2. From 3 to 4, it changes by 1. And from 4 to 6, it changes by 2. So each time, I'm going to look for my change in y over my change in x. Okay, so this one I would have 5 over 2, which I can't reduce, so it just stays 5 over 2. Then on the next one I would have 5 over 1, which I can reduce to 5. And then on the last one I have 10 over 2, which I can reduce to 5 as well. So these two are the same, but the top one is different. So because the top one is different, then I would say, no, this is not a linear function. And then on the last one, it says, is the table a function? So all of the x's are different. So I would say, yes, it is a function. The reason is all x's are different. And on the is it linear, we have to look at the change in y over change in x. So from 6 to 8, it changes by 2. From 8 to 13, it changes by 5. And then from 13 to 15, it changes by 10. So then on this side, from 1 to 2 changes by 1, 2 to 4 changes by 2, and 4 to 6 changes by 2. So we put our change in y over our change in x. So 2 over 1 reduces to 2. 5 over 2 would be the next one here, and that does not reduce, so I leave that alone. And then the last one is 10 over 2, which would reduce to 5. So I have this rate of change is 5, this rate of change is 5 over 2, and this rate of change is 2. So because they're all different, I would say no, it's not linear. Okay, so this one is basically the same thing, except for now we have a list of ordered pairs instead of a table of ordered pairs. So I'm just going to take the ordered pairs that I have here and put them into a table. So my x values go in that column, my y values are going in that column. So I have 2, 4, 5, 3, 8, 2, and 11, 1. So it says, is the relation a function? So I can tell that it is a function because all of the x values are different. So yes, it is a function. And the reason is all x's are different. And then to see if it's linear, we got to check the change in y over the change in x. So each time here, my y value is going down 1. Each time on this side, my x value is going up by 3. So each time, my change in y over change in x is negative 1 over 3. So because it's the same thing each time, I would say yes, it is linear. Okay, so then for number 11, I'm going to take my ordered pairs and put them in a table again. And first of all, is the relation a function? Well, because none of the x's repeat, I know that the relation is a function. And the answer y is all x's are different. And to see if it's linear, I've got to check to see what the change in y over change in x is. So from 10 to 4, the change is -6. From 4 to 2, the change is -2. And from 2 to 0, the change is -2. Then from -10 to -5, it goes up by 5. From -5 to 0, it goes up by 5. And from 0 to 5, it goes up by 5. So for the change in y over change in x, I would have -6 over 5, and then -2 over 5, and then -2 over 5 again. But because this first one is different, even if there's just one that's different from the other ones, you would say, no, it's not linear. Okay, so last example here. I'm going to put them in a table. I have 3, 5, 5, 4, 7, 3, 9, 2, and 11, 1. So all of the x's are different, which tells me, yes, it's a function, and that's the reason. Okay, and then to see if it's linear, I'm going to look to see what the rate of change is. So from 5 to 4, it goes down by 1, down by 1 again, down by 1 again, and down by 1 again. So it goes down by 1 each time. And then for x, it goes up by 2, up by 2, up by 2, up by 2. So each time my change in y over change in x for all of these ordered pairs is -1 over 2. So therefore, yes, it is linear. All right, so homework 5-1 is page 300, number 2 through 8 even, 14 through 20 even, and 64 through 72. And we will work on that in class together.